Welcome to the EPG Padashala, the lecture series in computer science for the postgraduate program. We are on module 37 of the paper compiler design, where we will talk about iterative data flow analysis. The objectives of this module are to learn to compute the in and out of the data flow equation component for reaching definitions, and to learn to compute the available expressions and live variables in the context of data flow equation also. Approach, we already know that there should be a conservative approach, and the approach is to calculate the in and out functions simultaneously for each node of the flow graph, and gen and kill are essentially same. What a particular definition is being generated and what gets killed is the same. Here our earlier module talked about the forward equations in terms of statement per statement, and here we will talk about in the context of computing it on a block wise. Not only that, we will also look at a backward equation based approach, where we will assume the in of every block, okay, the out of every block is assumed and the in of every block will be computed, and with a new in again we will compute the out, and we will keep on iterating till we will be able to come to a closure on whether the out is going to be correct or incorrect. Okay, between two successive iterations, if the value of out does not change, then we will call that as your actual out value. So, earlier we have talked about the forward equation where we are computing out based upon the in. Here again the equation has not changed, but the assumption is we will compute in, okay, and based on the new in we will compute the out of every block. Now, the operator which is called as the confluence operator is used here, and the union operator is the confluence operator here, which is going to be influencing the data flow equation, and it computes the union of all definitions reaching a particular point. So, here in of B, now we are resorting to the block representation rather than on a statement per statement, because your input will be a control flow graph, okay, and therefore based on the control flow graph you will try to group the statements into blocks itself, okay. So, a single block will be looked upon as a statement, So, whatever we have talked about with reference to statement per statement is now looked upon with reference to block by block. So, one particular block will generate some statements, the other block will basically, the assumption is you will not have multiple definitions of the same statement within a particular block, that is already known to us, okay. So, using the basic block algorithm which we have already computed, one particular block will not have redefinitions of the same statement, it is a meaningless situation. So, that is also going to be used here. Now, what happens is your assumption is in of a particular block is computed as union of the out of all its predecessor block, okay. Something will come in, for example, block B1 is there, block B2 is there, B1 will have an input to B2 definitely, right. So, in of B2 is computed as union of out of P, P in the sense P is a predecessor block here. So, which is in our example it is block B1, but why am I looking at all predecessor block? Multiple informations, multiple blocks could basically come into a single block. So, I have to compute union of all the outs to compute the in of the current block, okay. So, that is why this is this is a definition which is going to be used in this particular module. Then after computing this, out of B will be gen of B union in of B minus kill of B. So, after computing the new in, you can use that in to compute your actual out of a particular basic block. Now, again it is done block by block, it is not done statement by statement. Whatever we have defined as statement, now it is converted to a particular block. And a graph with n blocks will have 2n equations of this nature, and these equations have to be solved and are solved assuming that they are going to be recurrences, okay. So, the algorithm here is your input will be a flow graph for which kill of B and gen of B have been computed. So, we have already computed gen of B and kill of B in the previous module, where we have looked at statement by statement. We will do the same thing in the context of basic block. That is your input, and output will be in and out of every block, okay. The approach is the in of basic block B1 is assumed to be null is null for all blocks and converging to the desired values of in and out basically, okay. So, what do we do here? This is the algorithm. Initialize in of B is equal to null for all blocks B, okay. Then for each block B, you initialize out of B is equal to gen of B. Now we already computed gen and kill, right. So gen is assumed as out is assumed as equivalent to gen itself. So you will compute gen of a particular block and assign it to out. So this is also done. Now you are going to use a flag variable which is called as change, and you assume it is going to be true. Now what do you do? While change, that is while as long as this parameter is true, you will reset to false here. Now you will compute for every block B, you will compute in of B is equal to union of out of P, where P is a predecessor block, and you assign old out is equal to out of B, and based on the assumption that out of B is gen union in minus kill, you have computed in here, right. So this in minus kill is already supplied, gen is also already supplied, you will compute a new out. Typically speaking, this out and the old out should not change. If it changes, okay, if out of B is not equal to old out, then you assume change is equal to true and then continue for the next iteration. So this is done for every block first, okay, and then you have to basically go to the while block. So this is a for each block, right. So you will set here for if out of B is equal to old out, then change is equal to true. Even if one block resets change to true, I have to go through this to find out the comparison between the old out and new out for all the blocks, okay. That is the situation here. So this algorithm is very simple, and this algorithm is the basis for the other two algorithms also, which we will be discussing in this module. So where you will assume initially out of B is equal to gen of B, and then you use a flag variable to iterate. So you compute in of B as the union of out of all the predecessor block, and you compute your new out based on this in, and you check whether the new out and the old out are same. If it is same, you continue for the next block, okay, you anyway continue for the next block, you come out of the while loop. If it is not same, you will reset the flag variable to true. Now let us take this example here. The same set of 7 statements which we have already done in the context of the earlier module has been repeated here, but I have grouped it in terms of blocks. So block B1 will have D1, D2, D3. Block D4, block B2 has D4, D5, and block B3 and B4 has statements D6 and D7. As you know that this is nothing but an if-else counterpart. Now this is B2, B3, B4 will together constitute a do-while block. So that is why after B3 also you will go back here, after B4 also you go back here. So as you could see that in of B1 is null, whereas in of B2 will be out of B3, out of B1 and out of B4. Again out of B3, out of B2 influences in of B3, and out of B2 also influences in of B4, okay. So B4 and B3 has its input from out of B2. So but out of in of B2 depends upon out of B3. So that is why it has to go through multiple iterations. So this is what we already had. Now this has been changed to we can either use a set notation or we can basically go with the bit vector representation. As I already said in the bit vector representation, the first bit corresponds to D1. Then I have 7 bits here to represent the 7 definitions. So D1 to D7. So D1, D2, D3, D4, D5, D6 and D7. So the corresponding bit will be set to 1 or not, depending upon what is the set result vector here. Now let us take this example. Block B1 has 3 definitions, D1, D2, D3, therefore it is set. Block B2 has 2 definitions, D4, D5. Block B3 defines D6, block B4 defines D7. Though B1 has got 3 statements, all the 3 statements are defining a variable of its own choice. Within a particular basic block, typically you do not define a variable more than once, okay. So that is why D1, D2, D3. Now the bit vector representation of this is setting D1, D2, D3 bits to 1 and resetting all the other bits to 0. Similarly, D4, D5 means setting D4, D5 to 1 and resetting the other bits to 0, and D6 will be setting D6 bit to 1, the remaining bits are set to 0, and D7 will be setting the bit D7 to 1. Now to compute kill, so as we already know that this definition here kills D4, D5, D6, D7 because this has got I, J and A and I. So, those 3 are defined here. So, this will definitely kill D4 to D7, that is a kill of B1. What is the kill of B2? Wherever I and G are available, I and J are available. I and J are available at D1, D2 and D7. So, that is why we have here, this is D1, D2, D7, this is D4 to D7. Similarly, B3 will be simply D3 because D3 defines A and D6 is also a definition of A and D7 defines I, D1 and D4 also defines I, therefore it is killed here. So, this is my example. Now, this is given as input to the algorithm for computing reaching definitions. Now, so as you can, I have already told, in of B2 is nothing but out of B1 union out of B3 union out of B4. Now, union is typically looked upon as a OR operator and subtraction is looked upon as a combination of intersection and complementing operator. That is A minus B is nothing but A intersection B complement. Okay. A minus B is nothing but A intersection B complement. Intersection is actually an AND operator and union is nothing but an OR operator. So, out of B1 is we have assumed to start with out of B1, out of B3 and out of B4 will have basically these 3 components only because it is equal to gen. So, out of B1 is the D1, D2, D3 bits to 1, out of B3 is D6 set to 1, out of B4 is D7 set to 1. So, therefore, here I have those as my implication. ORing of this will result in 111 because I have a 111 in the first 3, then D4 bit is 0 in all, D5 is also 0 in all, D6 and D7 are set 1 in these 2 respectively. Therefore, in of B2 is 1110011. Now, out of B2 will be gen of B2. This is one I am talking about only one situation inside block B2 inside the loop. Okay. So, here initially out of B1 is gen of B1 etc. Now, out of B2 will be gen of B2 union in of B2 minus kill of B2. Now, this is what is in of B2. Gen of B2, block B2 defines 2 statements D4 and D5, therefore, they are set to 1 and in of B2 is just now we have computed and kill of B2 is it defines D4 and D5, therefore, it is going to be setting, okay, D4, D5 are defined. Now, as you could see here, kill of B2 is D1, D2 and D7, okay, kill of B2 is D1, D2, D7. So, therefore, D1, D2 and D7 is kill of B2. Now, how do I compute this? So, I have to OR this, but before that I have to do this subtraction. A minus B is A intersection B complement, okay. So, A intersection is the AND operator, B I have to complement this. So, it is nothing but just take complement of this bit which is 110 0001 will be 001 111, that is change the zeros to ones and vice versa. And so, this should be ANDed, ANDing of these two will result in bit D3 set to 1 and bit D6 set to 1. Now, ORing of these two will result in 001 because this is 1 here and there is a 1 here, that is why these two are 1 and there is a 1 here and that is why this is a 1, D6 is a 1 and D7 is set to 0. So, this is how I compute. So, I have to compute this for all the blocks and ensure that, okay, as we can see that out of B2 is this now, the previous out of B2 will be just gen of B2 which is nothing but this one. So, 0001100 and this is not same. So, I have to go through this for one more iteration. Okay. So, till all the blocks will have 2 consecutive iterations the same result of out computation, I have to go through the algorithm more than once. Typically, it is solved in 2 passes or at most 3 passes on a normal situation. So, here this is what we have already got and for example, we said in of B, okay, is going to be all null to start with and out of B will be gen of B to start with. So, therefore, this is D1, D2, D3, this is D4, D5, this is D6 and this is D7. So, that is out of B. And in pass 1, in of B1 is null only, there is no change. Out of B1 is also the same thing, because there is nothing input to B1 back as from the predecessor other than the just in plain input. So, whatever is gen of B1, the same thing will be out of B1 also. But for B2, we have got this is what we computed just now. B2's input is this one, output is this one. This is what we have computed, because out of B2 will be what we said, it is out of, sorry, in of B2 will be out of B1, B3 and B4 we said. Therefore, this is changed. Based upon this, this value is changed. So, this value and this value are not the same. Therefore, out of B2, this has to go through one more pass. That is the understanding. So, with that in mind, we will compute, we will assume in of B3, which is nothing but out of B2. Okay, this out of B2 is fed as input here, and I will compute out of B3. Again, this is not same. Anyway, we are resetting. We have to go through one more iteration. Now, this out of B2 is given to in of B4 also. Based on this, I have computed out of B4 also. Now, this has to go through one more iteration. Again, as you could see, out of B1 will not change here also. Now, here out of B2 and the previous out of B2 are same. Therefore, it is not going to go through one more iteration here. And so is the case with out of B3 and out of B4. Now, what does it infer? Out of B3 is 111, okay, that is bit D4, D5, D6 is set, and if I look at out of B4, it is bit D3, D5, D6, D7 is set. So, therefore, if you follow one particular path, those variables will be available after exiting from this particular block, and if you follow an alternate path, what variables will be available, that is what is indicated here. Okay. So, this is used to compute the reaching definitions. The next one is on computing available expressions. Okay. So, available expression is basically used to identify common sub-expressions, and how do we handle this? Again, we have to compute a data flow equation for this also. Now, available expression is typically computed as an expression x plus y is available at a point P if every path from the initial node to P computes x plus y, and after the last evaluation there are no assignments to x comma y. So, this is the basis. We know that expression x plus y is available at a point P if every path from the start to point P computes x plus y, and after the last evaluation there are no assignments to x comma y. So, if there is an assignment to x or y, then the value will be different, therefore, you cannot use that as a common expression. Killing expressions is not the same as reaching definitions, because reaching definitions will be definitely reaching at a particular, will definitely reach a particular point, whereas in the process one expression's value if it could change, okay, if a particular variable's value could change, that would affect the expression's value. So, therefore, you cannot treat these two as a similar situation. So, what do you do that? We have to handle it in a different scenario. So, as I already said, this is used for computing the common sub-expression elimination optimization technique. Now, how do we handle this? Compute the set of generated expressions for each point in a block from the beginning to the end of the block. Okay. At the point prior to the block, assume no expressions are available. Okay. At a point, that is, we said that there is a point before every statement, right. So, at the point prior to the block, assume that no expressions are available, and at point P, if say for example, say A is set of available expressions and Q is a point after P where I have computed x is equal to y plus z, we form expression available at A as follows, like these two steps are used. Add to A the expression y plus z. So, you have to add this to the available expressions and delete from A any expression involving x. Why? Because x has now changed. So, the previous expression cannot be used as it is involving x. So, therefore, you have to delete x from A any expression involving x. So, here this should be done in order from top to bottom, that is I have to do this first and then I have to go for deletion of an expression, deletion from A any expression involving x. So, I should not do it in the other way, that will result in some ambiguity. So, the order should basically be maintained. So, you have a set of available expressions and Q is a point. For example, at point P you have something, and supposing at the next point Q you have this expression available. Now, at this point what we do is we have to add y plus z to the available expressions list and then delete from A the expression involving x as the one of the operands. Now, let us take this example. These are my statements and these are my points. Okay. This is the first statement, so I say that none is available, no expressions available. So, A is equal to B plus C. So, I have to add this B plus C to my available expressions and I have to remove expressions involving A. Nothing is there, therefore, I do not do anything. The next one is B is equal to A minus D. So, what will I start with? I will add A minus D here, but B plus C is already there, but the next step says delete from the expressions anything involving B. So, B plus will be removed here at this particular point. Then I will add C is equal to B plus C. So, what will I do? I will first add B plus C, okay, and then remove expressions involving C. Therefore, I will remove B plus C itself. Now, this is the classic thing why we said that order should be maintained. If the order is not maintained, I have already recomputed the value of C here. So, B plus C cannot be used as a common sub expression. So, therefore, this should be avoided. So, I will add first B plus C, okay, and then I will basically remove expressions involving C. Therefore, B plus C will be removed right away here itself. So, again still I have at this particular point only A minus D. So, the last one is A minus D. Now, what happens is A minus D is a common expression. So, I am not computing this, but beyond this point nothing is available, that is the conclusion. Beyond this point nothing is available because I am recomputing D here. Okay. So, this is the available expressions computation. Now, the algorithm for available expressions, assume that U is the set of all expressions appearing on the right of one or more statements. So, you have a block and you have all the expressions available and you form it into a set called as U. Now, E gen of B, that is, this is expression generated of B is generated by a block, for example B, and E kill of B is set of expressions in U killed by B. Okay. So, E kill of B means what we have used one procedure, right. So, for that I have to compute for every block like that. So, after this particular block what is available should basically be computed as E kill, and out of B will be E gen of B union in of B minus E kill of B. This is the same thing only. I have simply replaced gen with E gen and have replaced kill with E kill. Now, in of B is now computed as intersection of, this is against the earlier one where we had union, we have now intersection of out of P for P being the predecessor block, which means that an expression is available at the input of a block only if it is available at the end of all of its predecessor blocks. So, supposing the same thing is computed at multiple positions, okay, and that gets input to a particular block. So, we say that that expression is available for this block only if it is available at the end of all of its predecessors. This is the assumption here, and the assumption here is in of B1 is equal to null, again the same thing which we have already done. Now, again the input to this thing is a flow graph G with E kill of B and E gen of B for each block, and output will be the set in of B for each block B. Okay. So, output will be the in of every block, because we want to know what expressions are available at a particular point of time to avoid recomputation. Okay. So, in will be the given as the output to this particular from the algorithm. So, in of B1 is null and out of B1 is equal to E gen of B1. So, this is the first statement assumption only. I am not assuming for all blocks of B as we did in the reaching definition situation. And for B not equal to B1, out of B will be union U minus E kill of B. Now, what is U? U is the list of available expressions already we have, and what is killed by that should be subtracted, and that will be out of a particular block B. Now again this B should not be equal to your B1, which is the first block of your control flow graph. Again you are going to use a flag variable called as change, and here change is equal to false. Again we are resetting change, assuming that it is not available between successive iterations, and for each block B not equal to B1, input of B is equal to intersection of out of P, where P is a predecessor block. So you compute in and you assume old out is equal to out of B, and out of B is computed as it is. Now if the old out is not equal to the new out, then you change, then you reset this variable to true, and then you go for one more iteration. So again this will go through multiple passes. The difference being I will be anyway recomputing in, but the computation of in alone is basically changed, and how we computed out for every block as an initial setup is also going to be changed for this algorithm. Now with that we can basically compute the available expression. So as we already have explained how to compute the initial generated situation, that is done first, and then you will also have the kill information available, which is computed as follows to get your final out computation for every block, which is nothing but the list of available expressions. So available expressions have to look at the RHS, definitions will look at the LHS. Okay. Available expressions, RHS will be added to the list, but LHS will also be looked upon to remove from the list of available expressions. Okay. So that is very important. The next one is live variable analysis, where we have to find out whether for any variable x and point P, whether the value of x at point P could be used along some path in the flow graph starting at P. X is live at P, else x is assumed to be dead at particular point P. Now the variable should be living. This is what was used as a basis for your register allocation computation. So you have to find out whether for any variable x and point P, the value of x at P could be used along some path in the flow graph starting at P. So x is said to be living at P, else x is said to be dead at particular point P itself. Now to do this we have 4 computations. In will be the set of variables live at a point immediately after before block B. Out of B will be the same at the point immediately after block B, and define of B definitely assigned values in B prior to any use of the variable in B. So definitely assigned, for this you have to compute reaching definitions, and use of B will be set of variables whose values may be used in B prior to the definition of the variable. So this is very important, it should be used before the variable is being defined, that is what we call as use of B. Now in of B will be use of B union out of B minus definition of B. The understanding is a variable is said to live coming into a block if either it is used before redefinition in the block, or it is live coming out of the block and is not defined in the block itself. Okay, that is your in of B. Okay, if it is not defined in the block and it is live coming out of the block, okay, this is what we call it, and use is it is being used before redefinition in this particular block itself. And out of B will be union of in of S, for all S being successor of B. So union of in of S for S being successor of B, that is going to be your out of B. Okay. So whatever comes into it, that will be the situation here. So variable is live coming out of a block if and only if it is live coming into one of its successors. Okay. It should be used by something else. Okay. Then only we can say that it is going to be living. So the algorithm is a flow graph with def and use computed for each block. The output will be the out of B, set of variable live on exit from each block. Now for each block B, do in of B is equal to null, while changes to any of the ins occur. Again this is going to be similar to using a flag variable. For each block B, begin out of B is equal to union of in of S, where in S is the successor block here. Okay. And in of to start with in of B is alone null, and in of B is equal to use of B union out of B minus definition of B. This is the computation of that. Now the example for liveness is not here given. R1 is equal to R2 plus R3 and R6 is equal to R4 minus R5. R4 is 4 here in this path, R6 is 8 in this particular path, R6 is equal to R2 plus R3 and R7 is equal to R4 minus R5. Take this scenario. At this particular point what happens, R2, R3, R4 and R5 are all live as they are consumed later, okay, and R6 is dead as it is redefined later. So here at this particular point R2, R3, R4, R5, it is defined here, okay. So we say that it is going to be used by, it is used here, which means it could basically be living for the successor blocks also. But R6 is assumed to be dead here as it is redefined later also, and R4 is dead as it is redefined here at this point, okay. At this point we see that there is a value for R4, but at this particular point on the alternate path R4 and R6 are basically going to be redefined here, therefore R4 and R6 are said to be dead, okay. But R2, R3, R5 can be live here. At this particular point, okay, R6 is redefined, okay. So what is the scenario here? I am redefining R6 here, I am redefining R6 here also. So this statement R6 is equal to R4 minus R5 will basically be a useless statement, because anyway both the paths is not using R6 but it is redefining R6. So it has to basically be, this is going to be a dead code. So I have to eliminate the dead code information. Now definition and use could also be computed, where we will say use of B is use of B union Y, provided Y is not in definition of B, okay. Definition is, it is being defined by a particular statement, okay. So definition of B is equal to definition of B union X, where X is going to be on the LHS. So you say it is defined, and I will say Y will be included in use provided Y is not going to be defined. So if I am using a particular variable, I should not define it in that particular block itself. So this is the computation of definition and use. So based on this, we have already seen this example in the analysis. So here what happens, B, C, D, F are the input to this particular block. Now the definitions of this block are A, D, E, they are defined here, and the use of this block are B, C, not D, because D is also defined here, and F. B, C, F are going to be, B, C and F are used here, and A, D and E are defined here, okay. So based on this I can compute the out as A, C, D, E, F, where A, C, D, E could go here and A, C, D, F could basically go here. So this is the situation. So use of B1 is B, C, F, definition is A, D, E, in of B1 is this one, and which is nothing but B, C, D, A, F. Again based upon this in, I have to compute the out, and that will be used for further computation. So on summarizing this module, iterative data flow equations have been used and studied for reaching definitions, available expressions and live variable analysis, and we have looked at the algorithm and examples for these three scenarios, and we have also looked at some computation that is going to basically be happening, and we will look at further data flow equations in the subsequent modules. Thank you.